Surprisingly, a single slit will produce an interference pattern not exactly the same as a double slit pattern, but similar. What we would expect to see is just a bright spot in the middle, and we actually do get a bright spot in the middle. Over here is the intensity graph of what we would see on the screen, and you do see that there's a big intense spot in the middle. But there are some smaller fringe patterns, and every single point throughout this slit acts like a Huygens emitter, and you get many rays of light that at certain angles will cause bright spots and dark spots. The width of the slit over here, A, is a factor. The relationship between the slit width, the angle, and the wavelength is very similar to what you see in two slits, but there's a very important difference. The slit width times the sine of the angle for a bright spot is equal to m plus a half times the wavelength. Remember, in double slit interference, it was m times the wavelength that got us a bright spot. For a dark spot, it's m times the wavelength. So the right-hand side of the equation is flipped for a single slit interference. You can still combine this with your screen parameters. If you have the length and you want to know the distance, the y's to certain dark or bright spots, the ratio of y over L is still equal to the ratio of the optical path length difference over the slit width in this case. And so this would be for bright, and you would have this for the dark spots. Let's do a practice problem. Let's read the question. Light of wavelength 750 nanometers passes through a slit 1 times 10 to the negative 3 millimeters wide. How wide is the central maximum, A in degrees and B in centimeters, on a screen 20 centimeters away? I'm going to draw a picture here. Here's my slit, and out here is my screen. Okay, we're going to have a central maximum followed by some fringes. And we want to know the width of the central maximum. So in terms of an angle, I'm talking about something like this. So this would be the angle I'm talking about. And as far as the width, that would literally be a distance from here to here. The way to think about this is that the width of the bright spot is basically the distance from the dark, between the dark spots on either side. And so if I could find the angle to the first dark spot and double it, I know the total angle of the width. If I find the y, or the distance from the center to the first dark spot, and double it, I'll know the total width. The angle that we're looking for is 2 times the angle to the first dark spot. And the width of the central maximum is 2 times the y dark for the first spot. And let's write down the numbers. So I have the wavelength is 750 nanometers. I have that the width, A, is 1 times 10 to the negative 3 millimeters. And I also have that the screen is 20 centimeters away. I need all these numbers to be in meters, so let's do some conversions. This one gives me 7.5 times 10 to the negative 7 meters. This one gives me 1 times 10 to the negative 6 meters. And this one here will give me 0.20 meters. Now I've got something I can work with. Now the angle formula, the sine of the first dark angle is equal to m times the wavelength, and the m is 1 for the first dark spot. So, oops, left out the a, that goes on this side. A times the sine of the dark angle equals the wavelength, which means that the sine of that angle is the ratio between the wavelength and a, and the angle itself will be the inverse sine of that ratio. And if I put the numbers in, that's the inverse sine of 7.5 times 10 to the negative 7 over 1 times 10 to the negative 6. And of course these are meters. Can't forget our units. And that comes out to 49 degrees. Now we need to double that. So if I double that, I'm going to get 98 degrees. This is the width in degrees of our big angle over here. Pretty wide, actually. Alright, for part B, we cannot use the same approximation that we used for double slit interference. What we have to do here is we have to understand that if the screen is over here and the slit is over here, that this y over L is not approximately equal to the sine of the angle. It actually is the tangent of the angle. So I would have to write that the tangent of this angle equals y over L. And that means that the y would be the L times the tangent of the angle that we just found before. And I can't use the angle 98. I have to use the 49 and then double the answer. So I will get that the L of 0.20 meters times the tangent of 49 degrees comes out to be 0.23 meters. And again, we have to double that, so we get 0.46 meters to get the whole width. And converting that to centimeters, I get 46 centimeters.